In the years immediately following the Second World War, Britain's railways were in a state of considerable exhaustion. The network had been worked relentlessly through the conflict, and much of the steam locomotive fleet was worn out, overdue for replacement, and expensive to keep running. Coal quality had become inconsistent, and the infrastructure supporting steam traction demanded enormous ongoing investment in depots, water troughs, and coaling facilities. Something had to change, and engineers across the world were looking in the same direction. Gas turbine technology had proven itself spectacularly in aviation during the war years, powering a new generation of jet aircraft that rendered piston engines obsolete almost overnight. The question that naturally followed was whether the same principle could be applied to railways. A gas turbine could generate enormous power from a compact and relatively lightweight unit, and it burned liquid fuel rather than coal, which promised cleaner and simpler operations. Switzerland was among the first to explore the idea seriously, and across the Atlantic, the United States was conducting its own experiments with gas turbine locomotives on freight railroads. Britain was not about to be left behind. The Great Western Railway had already begun investigating gas turbine traction before nationalisation in 1948. And when British Railways came into existence, it inherited both the interest and the ambition. The new organization saw gas turbines as one of several possible paths away from steam, alongside diesel and electric traction, and it was willing to invest in finding out which technology would prove most suitable for British conditions. Over the following decade, British Railways would commission and test not one, but 3 gas turbine prototype locomotives, each representing a different approach to the same fundamental challenge of converting the power of a spinning turbine into the motion of wheels on rails. The third and most ambitious of these machines would take the concept further than anyone had attempted before. The first of the 3 gas turbine prototypes to arrive was number 18,000, built by Brown Boveri in Switzerland and delivered to the Western region in 1949. It was an imported design, a product of Continental Engineering tested on British metals, and it generated around 2,500 horsepower from its turbine. Number 18,000 was put to work on express passenger services out of Paddington, running alongside the Great Western's aging fleet of steam locomotives on routes to Bristol and Plymouth. It demonstrated that a gas turbine could indeed haul mainline trains at speed, and in that narrow sense, it was a success. The second prototype, number 18,100, followed in 1951 and was built domestically by Metropolitan Vickers in Manchester. It took a different approach to the engineering, producing around 3,000 horsepower and using electric transmission to deliver power to the wheels. Like its predecessor, it was tested on Western region services, and it, too, proved capable of moving heavy trains at respectable speeds over demanding routes. But both machines revealed a problem that would haunt every gas turbine locomotive ever built. At full power, the turbines performed impressively, but railways do not operate at full power most of the time. At partial load, which is where a locomotive spends the majority of its working life, fuel consumption was dramatically worse than an equivalent diesel engine. The economics simply did not favor the gas turbine under normal operating conditions. Neither prototype was an outright failure, but neither made a convincing case for further development along the same lines. Number 18,100 was eventually converted into an electric locomotive, which is itself a rather telling indication of where confidence in the technology was heading. Despite these mixed results, however, there were engineers who believed the efficiency problem could be overcome with a fundamentally different design approach. At the Vulcan foundry in Newton-le-Willows, English Electric was already working on precisely that. The man behind the project was Vulcan foundry engineer J.P. Hughes, who had begun working on the concept in the early 1950s. His idea was bold and quite different from anything that had come before. Where the earlier gas turbine locomotives had used electric or mechanical gearbox systems to send power to the wheels, Hughes wanted to connect the turbine directly to the driving wheels through coupling rods, much like a steam engine. In simple terms, He was taking a jet-style engine and fitting it into what was really a steam locomotive body. The result was GT3, which stands for gas turbine number 3, and it took nearly a decade to complete. When it finally rolled out of the Vulcan foundry in 1961, it looked for all the world like a regular steam tender locomotive. It had the same familiar shape, the same wheel layout, a 460 arrangement, similar to the British Rail Standard Class 5. But where a steam engine would have had a firebox and boiler, there sat an EM27L gas turbine producing 2,700 horsepower, or around 2,000 kilowatts. And where the tender behind a steam engine would have carried coal and water, the GT3's tender was filled with kerosene. The whole machine weighed in at 125.5 tons, could reach a top speed of 90 miles per hour, and was finished in a plain red oxide livery. It was a striking thing, familiar, yet deeply unusual at the same time. One important detail, however, is that GT3 was not built because British Railways asked for it. English Electric had designed and constructed the locomotive at its own cost as a working showpiece, a way of proving the concept and selling the idea to the National Railway. It was a pitch, not a commission, and that difference would matter a great deal when the time came for decisions to be made. British Railways began testing the GT3 at its Rugby Locomotive Testing Centre, where the machine was run on static rollers to measure its power output and performance under controlled conditions. The results were encouraging. The turbine delivered strong and consistent power, and the direct mechanical drive that Hughes had designed worked as intended. From Rugby, the locomotive moved on to line trials, first on the former Great Central Main Line around Leicester, and then on the West Coast Main Line, where it was tested over the demanding Shap Incline in Westmoreland. On the open road, GT3 proved itself a capable machine. It could haul heavy passenger trains at speed, and it handled steep gradients with the kind of raw pulling power that only a 2,700 horsepower engine could provide. In terms of pure performance, there was very little wrong with it. But testing also made the problems harder to ignore. The same weakness that had troubled the earlier prototypes appeared again here. At full power, the turbine was impressive, but the moment demand dropped, the fuel consumption became very poor. A diesel engine can idle efficiently and respond to varying loads without wasting much fuel. A gas turbine cannot. It burns through kerosene at a high rate, regardless of how much work it is actually doing. And since a locomotive on a real railway spends much of its time coasting, braking, waiting at signals, and running at less than full effort, this was a serious drawback. There was also the noise. The turbine produced a high-pitched whine that was far louder than anything railwaymen or passengers were used to. And then there was the operational problem that no amount of engineering could fix. Because GT3 was built like a steam locomotive, with a cab at one end and a tender at the other, it could only run properly in one direction. It needed turntables to be turned around, and British Railways was pulling turntables out of service across the network. While GT3 was being put through its trials, the world around it was changing faster than its designers could have hoped to keep up with. The 1955 Modernization Plan had committed British Railways to a vast program of replacing steam traction with diesel and electric power across the entire network. Orders for hundreds of diesel-electric locomotives were already being placed and delivered, and the first electrified main lines were taking shape. This was not a distant plan or a cautious experiment. It was a transformation already well underway by the time GT3 turned a wheel in anger. The irony was not lost on anyone at Newton-le-Willows. The Vulcan foundry, the very works that had built GT3, was at the same time fully engaged in manufacturing diesel-electric locomotives of several different types for British Railways. English Electric was producing machines that were in direct competition with its own gas turbine prototype. Among them were components for the famous Deltic locomotives, which were proving themselves on the East Coast Main Line as some of the most powerful and reliable diesel Electrics in the country. The economic case was becoming impossible to argue against. Diesel electrics were more efficient at the variable loads that real railway operations demanded. They were simpler to maintain, required no special fuel infrastructure beyond the diesel supply that was already being rolled out nationally, and crucially, they could run in either direction without needing to be turned. They were also being built in large enough numbers to bring the cost per unit down to something manageable. Gas turbine traction, for all the raw power it could deliver, sat in an awkward position. It was more complex than diesel, less efficient in everyday use, and demanded kerosene supplies that the railway had no reason to provide for a single prototype. British Railways made the only practical decision available to it. At the end of 1962, the GT3 was returned to the Vulcan foundry. No further gas turbine work would be pursued. Back at the Vulcan foundry, the GT3 sat idle with no purpose and no prospect of further use. Over the following months, it was gradually stripped of any components that held value or could be repurposed. The turbine and mechanical parts slowly removed until what remained was little more than a shell. There was no preservation movement waiting to save it, and no museum with space or interest in taking on such an unusual machine. It simply waited, growing less complete with each passing season, until a decision was finally made about its disposal. In February 1966, the GT3 made its last journey, towed from Newton-le-Willows to the Thomas W. Ward scrapyard in Salford. The locomotive that hauled it there was a British Rail Standard steam engine, one of the very machines that GT3 had been designed to replace. Both were heading toward the same fate, overtaken by the diesel and electric traction that had proven itself the practical choice for Britain's railways. It is a small detail, but one worth pausing on. The gas turbine experiment in Britain ended not with a dramatic moment of failure, but with a quiet disappearance. No part of GT3 survives today. There is no preserved example in a museum, no recovered turbine in a private collection, nothing at all to show for a decade of engineering work beyond photographs and paperwork. It is worth noting, however, that the idea of gas turbine traction did not die everywhere. In France, the original TGV prototype ran on gas turbines before the program switched to electric power, and North American railroads experimented with the concept well into the 1960s. But in Britain, the story ended at Salford in 1966, with cutting torches and scrap metal. We hope you have enjoyed this look at the brief and rather sad life of a locomotive that worked, but simply arrived at the wrong moment in history. Thanks for watching. Please like, share, and subscribe for more videos covering unusual British locomotives.